Hello everyone, we continue with example 6. So we find the point at which the line with parametric equations are given here intersects the plane for x plus 5y minus 2z is equal to 18. So we substitute the expression for x, y and z from the parametric equations into the equation of the plane. You see, actually geometrically our aim is to find the intersection point of the line and plane given in the example. This is the plane and line will be, for example, in this form, and our aim is to find this point, which is the intersection of the line and plane. So in order to find the intersection point, of course we will get a common solution for the equations of the line and plane. For this, we write the parametric forms of the variables x, y, and z using the parametric equations of the line into the equation of the plane, you see. And from here we find the value of t, which is equal to minus 2 easily. And therefore, the point of intersection occurs, this one, when the parameter value is t is equal to minus 2, which means from the parametric equations of the line we find the intersection point as minus 4 8 and 3. They are the components of the intersection point. Two planes are parallel if their normal vectors are parallel. Geometrically, these planes are parallel because the normal vectors are parallel. This is the normal vector n1 for the first one. This is the normal vector, let's say n2 for the second one, and n1 and n2 are parallel. They are actually in the same direction. By moving this one to here, we get the same direction. The positions are different, therefore they are parallel planes, which means we don't have any intersection point for these planes. Okay, for example, the planes given by linear equations are parallel because their normal vectors are n1 and n2, like this one is equal, it satisfy the equality n2 is equal to 2n1. Namely, if one of them is a multiple of the other, like this one, namely n1 is a multiple of n2, or n2 is a multiple of n1, so we say the planes are parallel. By taking the coefficients of the variables x, y, and z easily, we find the components of the normal vectors of the planes. From the first one we have 1 to minus 3. From the second one we have 2 for minus 6. And easily you see n2 is 2 times n1. n2 is a multiple of n1, therefore they are lying in the same direction, therefore the given planes are parallel. But if two planes are not parallel, then they intersect in a straight line, like this one. You see, we have two planes here and the angle between them is theta. Actually, also this is the angle between the normal vectors, because the normal vector of the base plane is n1, you see, n1, and n2 is the normal vector of the second plane, and the angle between them is theta, which is also the angle between the planes, and the intersection points of them is the line here. Okay, actually this is the base plane, for example, and we have the second plane like this. Okay, we have an intersection point, intersection line for the planes. Okay, if two planes are intersecting, so we get a line like this. Then they intersect in a straight line, and the angle between two planes is defined as the acute angle in this one. Okay, this is the angle of the planes. They are not parallel between their normal vectors actually. So find the angle between the planes given here, and find symmetric equations for the line of intersection of these two planes. Namely, we will find the equation of the line which is the intersection of the given planes in the example. First, we need to find the normal vectors of them. Normal vectors are found by taking the coefficients of the variables x, y, and z respectively. From first one, we have 1, 1, 1 for the normal vector of this plane, which is stated as n1. Similarly, n2 is given here by using the coefficients of the variables. And theta is the angle between the planes, gives actually it is the angle between the normal vectors. By using the geometric interpretation of the inner product, you know, n1 inner product n2 is equal to the length of n1 and the length of n2 times cosine theta, if you remember, and from here cosine theta becomes the inner product over the multiplication of the lengths of the normal vectors here. Computing them, we get 2 over square root of 42, and taking the arc cosine, we get theta is arc cosine 2 over square root of 42, which is approximately equal to 72 degree. In order to find the angle for the planes which are not parallel, it is enough to find the angle of the angle between the normal vectors. So for the second question, we need to find first a point on L, you know, to find an equation or symmetric equations of the line. First, we have to find at least one point on this line. So how can we find? Since this is the intersection of these two planes, choosing a value for one of the variables in here and obtaining a common solution for the other variables, we obtain a point on this line. Therefore, we set z is equal to 0 in the equations of both planes. So this gives the equations x plus y is equal to 1 and x minus 2y is equal to 1. Okay, we choose any variable from here. You can choose, for example, y, and you can write 0 for the variables y, and for the other variables x and z you can get a common solution for them, and you can find another point in the line which is the intersection of these two planes. Namely, we try to find a common solution for these two equations that involve three variables. So to get rid of one of them, we should write a number to get just two variables for two equations to solve easily. So from here we obtain x is equal to 1, y is equal to 0. Therefore, the point 1, 0, 0 lies on this line. So we know a point. So, and if we find also the direction vector of this line, we can find easily the equation of the line in every form. So we observe that from here also you can see this line lies on both planes. Okay. Therefore, the normal vector, this one, is also perpendicular to this plane. Also, this normal vector, which is the normal vector of the first plane, also perpendicular to this line. Okay, we have two normal vectors which are orthogonal to the line, which means if we get cross product of them, we get a vector which is parallel to the line, which is the intersection of these planes. Therefore, we take the cross product of the normal vectors of the planes, and we obtain a vector which is parallel to the line, which will be also actually the direction vector of the line. Therefore, the symmetric equations of the line, and we know 1, 0, 0, 1, x minus 1, y minus 0, z minus 0 over the components of the direction vector respectively. Okay. Another example, let's find a formula for the distance from a point to the plane. So now our aim is to find the distance between a point and plane. What is the distance? A point, let's say P0, to the plane. Okay, and the equation of the plane is given: ax by plus cz plus d is equal to 0. Okay, and P0 has in the example this point is stated as P1. Okay, P0 is the point on the plane. So how can we find the distance stated by bigger d in the example? By using the equation of the line and the components of the given point. So let P0 be any point in the given plane. We choose a point, we take a point. You can find a point by writing any values for x, y, and z, and they should satisfy the equation of the plane. You can choose and be the vector corresponding to the P0 and P1. By combining P0 and P1, we obtain a vector written here, you see, which is the blue vector. Okay, our aim is to find the distance between the point and plane, and we form a vector by using the points P0 and P1, and we know the normal vector of the plane, okay, which is the normal vector n, and it has the components a, b, and c. And from here we obtain the components of the vector b, x1 minus x0, by taking the difference of the points. First writing the terminal point of the vector b. So you can see the distance from P1 to the plane is equal to the absolute value of the scalar projection of b onto the normal vector. If you remember, the scalar projection of the vector b onto the normal vector will be the vector from here to the point P1. Okay, this is the projection, the projection of the vector b, and this distance is actually equal to the length of this projection, which is called the scalar projection of B onto the normal vector. Okay. Therefore, by using the formula for the scalar projection of B, which is written as n inner product B over the length of the vector n, and we know the components of the vector B, we know the components of the vector n. Therefore, we write respectively a times x1 minus x0, which is the multiplication of the first components, and has the components a, b, c. You see a times x1 minus x0, b times y1 minus y0, c times z1 minus z0 over the length of the normal vector written here. And from here we can rewrite the numerator ax1 by1 cz1 minus ax0 by0 and cz0, actually by writing x0 y0 z0 for x, y and z in the equation of the plane. So from here we have ax0 plus by0 plus cz0 is equal to minus d. So from here we write minus d, and we have another minus, they become plus d. So we have a formula for the distance from the point to the plane in three-dimensional coordinate system written here. Okay, just write the components of the normal vector and the point, the components of the point P1 here, x1, y1, z1, and we know d from the equation of the plane, and we can find easily the norm of the normal vector, and we obtain the distance from the plane to the point. And here you see an example for this, you can understand easily. And lastly, we will find the distance between two skew lines. Okay, as I said, they lie on the parallel planes like the box. This is the base plane of the box, and this is the top plane of the box. Okay, and a line is in this direction and another one is in this direction. So we don't have any intersection point for this, and they are not parallel since they are in the different directions. So how can we find the distance between them? What is the distance between them? So actually the distance between two skew lines are the distance between the planes, parallel planes. And we know parametric equations of L1 and L2. Okay, L1 and L2. So by taking, the cross product of the direction vectors of L1 and L2, we get a vector that is perpendicular to the direction vectors of the lines. Therefore, it will be a normal vector of these planes. Okay, this is the direction vector v1. For example, this is v2. The cross product of v1 and v2 will be the normal vector of the planes, because this will be a vector that is orthogonal to vectors v1 and v2. So by taking the cross product of them, and we can find easily by using the parametric equations the direction vectors of them. The direction vector of L1 has the components which are the coefficients of the parameter t. If you look at the parametric equations formula for a line, 1, 3, minus 1, and the second one is 2, 1, 4, has the components 2, 1, 4, And finding the cross product by using the definition, we obtain the components of the normal vector of these parallel planes, minus 6, minus 5. So if we put s is equal to 0 in the equations of L2, so we know the normal vector of the planes, and for the second plane we find it's also a point, and then we will find its equation for the second plane. So writing 0 for the equations of L2, namely we will find a point on the line such that we get a point on the plane actually. Writing 0 for S, we get 0, 3 and minus 3 on L2. So an equation for the second plane is found by writing the scalar equation formula, namely 13 times x minus 0 minus 6 times y minus 3 and minus 5 times z plus z minus 3 becomes z plus 3, or it is written in this form by rewriting. So we know the equation of the second plane, and if we find a point on the first plane, we get a distance from a point from this point to the plane, which means actually we find the distance between two planes or two skew lines. Okay, so we can find easily a point in the first plane by using the parametric equations of the line L1. Writing 0 for t, similarly we get 1 minus 2, 4, this one. So the distance between the lines is the same as the distance from the point to the plane. Okay, why do we say distance between the skew lines is same as the distance between the point to the plane? Because we have already a formula for a point and the plane in three-dimensional coordinate system. Using this easily we can find the distance between the skew lines since they lie on the parallel planes. Okay, by finding a point in one of the planes and finding the other the equation of the other plane, we get a distance between skew lines. From the point to the plane, by formula from here, ax1 by1 c z1 plus d, here a, b, c are equal to 13, minus 6 and minus 5, and the point is the point on the first plane has the components 1, minus 2, 4, and we use the equation of the second plane, therefore d is equal to 3, d is equal to 3, and we take the norm of the normal vector according to the formula, and we get the distance between skew lines, actually distance between two parallel corresponding planes. Okay, please send your questions to my email if you don't understand any part of this lecture note, and I can answer by using the email. Thank you very much.